You've been there, right? You send a crypto transaction and then you just wait. And you're sitting there wondering, why is this taking so long? Why does it cost so much? Well, get this. That slowness, it's not a bug. It's actually a choice. And today, we're going to unpack the incredible engineering trade-offs behind whether a blockchain is fast, cheap, or secure. I mean, if you've ever tried to use a really popular blockchain when everyone else is, you know exactly what I'm talking about. You hit send, and then nothing. You just wait. It feels broken, right? Like there's some kind of flaw in the whole system. But what if I told you it's not a flaw at all? That's really the big question we're tackling. I mean, we live in a world of instant everything, so why on earth are some of these transactions so slow and so expensive? The answer, it turns out, gets right to the very core of what a blockchain is.
All right, so let's just get right into it. That slowness we're talking about, it isn't a bug, it's a feature. Seriously, it's the result of a very deliberate, very calculated trade-off that engineers made. They decided to prioritize other things that are, you could argue, way more important, things like security and decentralization. So to really get a handle on that trade-off, we've got to pop the hood and look at the engine that runs the whole blockchain. This engine has a name. It's called the consensus mechanism. And there are really two main types that power almost every network you've heard of.
Okay, so what in the world is a consensus mechanism? The easiest way to think about it is like a rule book for the whole network. It's the system that lets thousands and thousands of computers scattered all over the globe, computers that have no reason to trust each other, somehow agree on one single version of the truth. You know, what transactions are legit and what order they happened in. It's a huge deal. All right, let's break these two down. Over on the left, you've got proof of work. Think of this one like a massive global competition. You have these miners with super powerful computers all racing to solve a really hard math puzzle. The first one to solve it gets to add the next block of transactions to the chain. Now look to the right. That's proof of stake. This is totally different. It's not a race, it's more like a lottery where you buy tickets with your own crypto. Validators lock up their own coins as a kind of security deposit. That's their stake. In return, they get a chance to be picked to approve the next block. If they follow the rules, they get a reward. If they try to cheat, poof, they lose their deposit. See? Two completely different ways of getting everyone to trust the system.
And these two different approaches, they have huge consequences. You can see it right here in the table. Proof of work, it's like the heavyweight champion of security. Super tough. But man, it uses a ton of energy, it's pretty slow, and the fees can go all over the place. Proof of stake, though, it's built from the ground up for efficiency. It's way faster, cheaper, and uses just a tiny, tiny fraction of the energy. And when I say a tiny fraction, I'm not kidding. Just look at this number. When Ethereum, which is the second biggest blockchain out there, made the switch from proof of work to proof of stake, its energy use dropped by over 99%. Let that sink in. That's not a typo. Over 99%. That's a complete reinvention of how much power the system needs to run. So that leads to a pretty obvious question, right? If proof of stake is so much faster and more efficient, why doesn't everybody just use it? Well, the answer is it's complicated. And it's because of this fundamental rule, almost like a law of physics for blockchains. It's called the scalability trilemma.
The blockchain trilemma. The basic idea, which was really popularized by Ethereum's founder Vitalik Buterin, is this. When you're building a blockchain, there are three amazing things you want it to have. But, and this is the killer but, you can only ever really get two of them at the same time. You always have to make a sacrifice.
So what are these three magical properties? Okay, first up is decentralization. This means no single person or company is in control. It's the whole point of blockchain for many people. Second, you've got security. This just means making the network super tough and expensive to attack. And third, there's scalability. This is the big one for speed. It's the ability to handle tons of transactions really quickly and cheaply, kind of like Visa or MasterCard. And the trilemma says, pick two. You have to decide which of these three you're okay with not having at 100%.
Okay, so if you're a developer and you're staring down this trilemma, what do you even do? Well, it turns out the industry is basically trying two main strategies to solve this puzzle. Think of it like traffic. You can either try to make the main highway bigger and wider, or you can build a super fast express lane on top of it.
Let's start with the first approach, making the highway bigger. This is what we call Layer 1. Layer 1 is the foundational blockchain itself. We're talking about networks like Bitcoin or Ethereum. It's the main road where every single transaction gets settled for good. The highway analogy is perfect here. It's super secure, super robust, but man, during rush hour, you get traffic jams. So if layer 1 is that congested highway, then layer 2 solutions are that express toll road built right on top. These are separate systems that work on top of the main blockchain. They handle a bunch of transactions off-chain, where things are way faster, and then they bundle everything up and settle it back on the super secure layer 1 highway all at once. So how exactly does this express lane work? Well, one of the most popular ways is something called a roll-up, and you can see how it works in this diagram. It's actually pretty clever. Over on the left, you have what's called a sequencer. It takes a whole bunch of individual transactions, hundreds of them, and basically bundles or rolls them up together. Then it just sends a single, tiny, compressed piece of data, a proof, down to the main layer 1 chain. It's like, instead of having 1,000 people all trying to get through the same door, one person just hands the guard a list that proves everyone is accounted for. Super efficient. And what's really fascinating here is that there are two totally different philosophies on how to prove that bundle of transactions is legit. On one side, you have optimistic roll-ups. Their motto is basically innocent until proven guilty. They just assume the transactions are all valid, and then they give people a window of time to challenge it and prove there was fraud. On the other side, you have ZK roll-ups. Their motto is the complete opposite: guilty until proven innocent. They use some seriously advanced cryptography to generate a mathematical proof that guarantees every single transaction in that bundle is correct right from the start. So one is based on social trust and challenges, the other is pure, cold, hard math. Okay, all of this, the layers, the roll-ups, the proofs, it all leads us to one final and maybe the single most important concept we need to talk about. With all these different systems, how do you know when your transaction is actually, well, done? Like really, truly permanent and can't be messed with ever again? That concept is called finality. Finality is the moment a transaction becomes completely irreversible. It's written into the ledger, it's set in stone, and nobody can alter it, reverse it, or cancel it. It is officially part of history. And as you can imagine, if you're sending a lot of money, knowing exactly when that happens, that's everything. All right, and this is where the rubber really hits the road. Just look at these numbers. This is time to finality. On Ethereum, a super secure layer 1, it takes about 13 minutes for your transaction to be 100% irreversible. Okay, not bad. But now, look down the list. Cosmos, about 6 seconds. Polygon, 2 seconds. Avalanche, 1 second. And Aptos is under a second. We're talking about the difference between brewing a pot of coffee and tapping your credit card. The difference in speed is just, it's absolutely massive. And you know, this whole idea of being forced to make these tough trade-offs, it's not some new thing that only exists in crypto. It's actually a classic, well-known problem in computer science. It's called the CAP theorem, and it basically says the same thing for any distributed network. You get 3 desirable properties: consistency, availability, and partition tolerance. But you can only ever have 2 of the 3. You just can't have it all. So here's the bottom line. How do those other networks get that insane sub-second finality? Well, a lot of the time, it's because they have a smaller, more exclusive group of computers, or validators, that have to agree. It's way faster when you don't have to ask for everyone's opinion, right? It's more efficient, but it comes at the cost of decentralization. And there it is. That's the blockchain trilemma, playing out right in front of our eyes, right there in the data. And that right there, that is the central conflict that's going to define the future of this whole technology. It leaves us with this massive, open-ended question. As all this evolves, what do we as users actually value more? Do we want that absolute, rock-solid, decentralized certainty, even if it takes a few minutes? Or do we want that instant, lightning-fast speed, even if it means sacrificing a bit of that decentralization? There is no single right answer here. And the choices that developers and users are making right now, well, they're going to shape the future of the internet for a very long time to come.